Thanks everyone again. So this talk is about a couple of memory leaks that I've seen and been part of Flipkart. Uh, let's jump right in, I think. So I'm asked not to type anything on the keyboard, but I do have to show some examples. So if it goes down in the middle, I'll have extra time, right? Like anyway, it's just Tejas talk next, so I think it's fine. The focus for this talk would be a typical web application, specifically the Flipkart.com application. Uh, and if you distill any web application to its core, it does three main things, right? It handles a request, fetches a bunch of data from other resources, and decompresses them as part of it, and transform that data into something else, right? And then like serialize and then send it out. So most of the web applications are basically a glorified string processors, effectively. So this is, I'll just like walk through very quickly what is the request cycle for Flipkart.com. Uh, so So in Flipkart, all the storefront pages, as we would call them, homepage, product page, search page, and actually recently we actually launched payments also on server side, which is kind of a different story altogether. So all of them are server side rendered, fully formed HTML that goes out to the client. So briefly, our request cycle looks like this. So core of the application is Express, React, React Router. Redux is used for state management. No fancy frameworks that we are using as so far. Thankfully we sort of avoided the temptation to rewrite everything every 6 months. So Express delegates the route matching to React Router and maps, which basically maps the root component, right? The whole React tree at that point to the path. The React component tree then gets a Redux store instance as a prop, and then it goes on. So the store instance gets filled with data from multiple JSON API calls. This I think like pretty common for most of the applications, I think. We make about 3 to 4 API calls. I'm sorry, I'm pointing to the slides. There is nothing there because they didn't want to put everything on the slides. So we make about 3 to 4 calls. First call is very important for the rest of the calls, and all the other calls, out of which like there is one API call tends to be a little bit heavy. So once the store is ready, we pass that. We basically give it to render to string, basically convert that into HTML. And we also serialize the Redux store that was built up till this point also into a JSON string, a huge JSON string. Put both of them together into a handlebars template, which also has links to preload CSS and other things, meta tags and all of that. And then everything goes out to the client, right? So I'm going to take you back in time a little bit here. The desktop web application of Flipkart.com was newly relaunched at this point. There was a time when the website was like taken down for reasons. So we were on the cusp of big billion days, which is kind of a big deal internally. Okay, no one gets it. The prep work involves many teams coming together to run load tests at very high scale to see how their application performs at a very large scale, which is not possible to do in a very small, at a team level, basically. In these runs, the aim is to understand the resource usage of sort of the holy trifecta of any web application: CPU, memory, and network. So our team was also doing this. The load tests were being run every day. Usually in the night, we kind of like do those load tests. And everybody was taking turns attending them and coming up with fixes for performance issues that were noticed. So at a certain point in this process, everything was seemingly stable. Like we fixed a few bunch of issues, and sort of it looked okay at that point. Load test with the default ramp up plan of throughput hitting almost about like we were targeting about 100K in the first BBD, like 100K requests per second. It was looking good, right? So one day there was a plan to do a spike test to simulate what were called flash sales at that time. So we have these like, people hate these things, but that's how we used to do it. It was needed at that time anyway. So imagine the same number of requests that I just like spoke about, 100K approximately, but within a fraction of seconds, right? So when everything happens at once, things change quite a bit. So the test was to see if, where, when, and how the application breaks or performs. But the application that supported the request rate before, the same request rate, now just like keeled over and crashed completely, right? Almost immediately, that too. Like I think if I remember correctly, it was like 4 seconds or something, after which it died. And it always crashed with a out of memory exception. How many of you seen this, by the way? Like, if you are running, yes, my crew. And I'm guessing like everybody has seen this in the build output, right? Yeah. TypeScript. The process used up more than 4 gigs of memory, while in all the other runs, it was not going beyond like 1.5, maybe 2 even. Since the entire stack was new to us, there were not a lot of obvious places to look into, and like, what was causing this memory growth, or even potentially a leak. We did not know whether it was a leak or just like, expected that this is the memory usage that the application should need. We could probably increase the memory allocation, and I know like since a lot of people, put their hands up that they've seen this error. Stack Overflow number one answer, what is that? Max wall space size, right? But that's not a solution to this in production especially. So I'm not going to be too technical here. Memory growth in an application is really okay. Depends on your application. But as long as it doesn't destroy the process or like, completely makes it unusable, I'm calling this a memory leak, right? For the context of this talk, I'm going to be using those words interchangeably, and I'm making that deliberate choice. So to demonstrate the problem, I've set up a simple application that's almost a fork of the original application that actually had this issue, but with all the sort of office code removed, right? It also renders a very comparatively smaller React tree as well. I can't walk you through all the code right now because we don't have time, but I'll share the slides and the notes and the code also later once it's completely sanitized and no code references. This application renders a simple comparison table between the populations of India and China, and completely on the server side. So it behaves like as if it's the same Flipkart.com website, I guess. And this is what the HTML looks like. Please don't crash. Yes, this is what the HTML looks like. The data is of this particular, the country data is powered by 2 mock JSON APIs. And to visualize the bug a little bit quicker, I've also artificially bloated up the response, matching like what we used to see at that time. And the API call sequence also is closer to what we had in the app. So in this case, the API, China and India APIs are different. So I make a call to the India API first and then the China one, and then like pass all of that to React, Redux, all of that. And so I have a demo also. I think we will have time. So the server is running at the top. The left panel here is the load test. And the right one, you'll see that just notice the memory thing that like it says like 52 MB at this point. So I'm going to run this. And ideally, if this works, this should crash. And if it doesn't work, it's okay. Everybody has seen that error already. So in dynamic memory allocating languages like JavaScript, Ruby, Python, even Java for that matter, allocations of objects typically happen on the heap mostly, right? And I'm simplifying here a lot. A lot of languages do have a lot of optimizations to make sure that it is not too heavy on that side. But in the most simplest way, just like we can assume that that's the case. And most of these objects in these languages also have references to other data types. The GC takes care of maintaining these references, cleaning them up, etc., when the application doesn't need it anymore. To understand how the memory heap changes, you have a bunch of options in the Chrome DevTools, which I'm going to open right now. Oh, this is not going to start, but I have these open already. So you have a bunch of options. The way to get to this is you run your application with node inspect, right? And you pass a flag called inspect to Node.js to your process basically. And this is the URL that you go to. You click on inspect for your application, which I can do right now. It doesn't do anything. I can't do anything right now because the application is basically crashed. Nothing works. But I've taken this. Okay, I'm sorry. Right, snapshots. So you have a bunch of options here. Heap snapshot, allocations on timeline, sampling, detached elements. So I'm running Chrome Canary, so you'll see the last one, which is new. Allocations, I'm not going to look at allocations and sampling at this moment. What I'm only going to focus is on snapshots. So snapshot, like the name suggests, takes a snapshot of the entire heap and presents it in a neat format in the UI. It's basically it looks something like this. The top section of the UI contains all the objects in your entire heap, sorted by the class that they are created with. While the bottom section, which is the most important one for this particular context, this talk at least, is all the references to that object. So the moment I select a different object, the references keep changing at the bottom, right? So, and you have to read it from bottom to top. So here in this case, a clear immediate thing is like holding on to references on timeout and all of that. So to figure out how and whether the object references are being held and hence leaking memory potentially, a good starting point is a 3-step snapshot process, which I've taken 3 snapshots here that you can see here. So the first snapshot typically is taken when the application is booted up and potentially even warmed up, right? So you maybe run some workload and then like take a snapshot. The second one is right after the issue starts manifesting. And the third one is taken after forcing a GC with that button. And the last step is very important here to distinguish between a probably genuine memory growth and memory leak or memory retention. If the heap space didn't change much, like you would see, like you're seeing here, between the 2 steps, right? Because we have run a GC, the expectation is that the third one should have less heap size, but that's not the case here. So basically, the application is holding on to references more than it needs to. So the memory tooling itself, this entire thing, contains options to view the objects that got allocated between 2 snapshots. So you can do a comparison view, which can help surface any references that were being held beyond a certain point. So I'm going to do that right now. So what I'm going to look at is the 2 snapshots, this snapshot specifically, and compare it with the first one. Because if I compare it with the second one, there won't be anything to see. So what I'm looking for here are patterns of my own application. I know a few things about my application, what objects get created, what shape of those objects contain, etc., etc. Right? So a good starting point here is looking for those kind of patterns when I scroll. So this is what I do. This is not probably the most efficient way to do this. This is what I do. And if you see here, this main bloat that you are seeing, I know that this is a response object that I'm sending from my API server. Somehow, something is retaining this particular object, or even in this case, like 28 objects, and we'll see what that is. So this bottom part is showing all this object is getting retained by this entire chain of events. So you see a promise here, then a bunch of promises, and then timeout, on timeout, idle next. So timer is an object in Node.js and even JavaScript. They're implemented as a linked list, right? So you have whatever you call, like set timeout, for example. That set timeout, whatever number that you have, there is a linked list created with that number and stored in a hash map. And whenever the timer expires, basically all the sort of functions get run. Right? That's why you see that there is a chain of mappings here. And what this points to is that there is a promise that then also has a mapping to the object that's getting retained. And this sort of narrowed down the problem space quite a bit, right? So we knew that there is a timer object in the API stack, API fetch stack that we were doing. So that's where we started looking into. And back to Keynote. Yeah, so this is the code that caused the bug. So what you see here is there is a timeout promise, actual promise, promise.race. So promise.race is an API that fulfills when at least one of the promises fulfill or resolve. It's almost the reverse of promise.all, right? This was a way to cancel a fetch before abort controller was a thing. Like cancel will fetch was not initially defined. So this code is from back then. I'm adding, the word cancel, like I'm adding scare codes to it because when the timer expires, right, before the actual fetch actually happens, the fetch is the actual promise is not actually cancelled. It's still in the pipeline. It's still going over the network. It's fetching all the data. It's just discarding all that data. But net, what we wanted to achieve with this particular API was sort of a fakey timeout, effectively. So what was happening here is and again, if you notice, we are not canceling the timeout, right? There is no clear timeout that's happening. So what was happening effectively was the main data fetch promise resolved much more quicker than the timeout, right? So the promise was holding on to the object, and that in turn was like getting held on to by the timer object. And because the entire response object was still in the heap, even though the request has actually finished by that time, the heap basically got bloated, and that's what was causing the crash. The reason why this was not happening during the normal load test when we did the good ramp up was because basically the timeout was set to some whatever time that it was set to. It was right. It was effectively closing all the timers in time, right? So just in time to ensure that the overall memory usage was not completely high, right? So the bug still existed there. It just did not manifest until we ran that spike load, because at that point, like a lot of objects were getting created. The fix here is super simple, like I said, timeout, clear the timeout. And then like we move on to much closer to where we are today. So this over time within our team, we have settled on a process to measure the performance of the application with a focus to understand the trend rather than just like focusing on the peak like we did before, right? And then it sort of evolved over time, and we sort of came up with some guidelines on how we run these test cases. It goes something like this. So we deploy a unit of the application to an isolated environment that's as close to production as possible. Obvious things. Since we have been doing this for some time, we know what's the good max throughput for the unit that we deploy, what it can handle. So we start the load test with a small number and incrementally go up in steps until that peak throughput is reached, plus a little bit delta, right? Plus a little bit extra. And we aim to do about 6 to 7 of these steps. So we go from 0 or maybe 10 requests per second to maybe 100 requests per second in like 6 divisions. And during each step, we note down the CPU saturation levels, the average and peak latencies also. And sometimes we also have to change the deployment units specification, like CPU, memory allocation, things like that. So we also note down that for future reference. And this is repeated every time. We have like data going back 2 years with this kind of information that I'm showing you here. And this is from a real and load test like that. This consistency in data going back years allows us to sort of better understand the trend, not just within the throughput targets like this, but also back in time, right? And this, in my experience, has been invaluable to understand and have a memory model of the application. In the ideal scenario, and again, what we are looking for in all of this is, in the ideal scenario, the CPU usage should scale linearly for each run, while the latency should ideally remain constant or at least consistent. And it will do that until a point where the latency starts increasing without any throughput of the application increasing. Right? At this point, we know that the application has reached saturation. You can't like go beyond that. And this year, we also followed a similar process very early on, because again, we sort of started doing this very methodically. And everything looked okay in our team level load tests. And we run these often enough. However, the team started noticing something was off back in May. There was an uncharacteristic increase in the average latency, and seeming it almost looked like a random change that happened, and we don't know like what was happening. It was not matching with our mental models, but also there was no discernible pattern at that time. It was not happening on all the machines all the time. Some machines were like slow, and we initially just categorized that as a hardware problem, and we said, okay, we'll debug this later. It used to subside and then come back up after a while. After a few weeks, though, the team noticed a pattern here. If there are no deployments beyond a couple of weeks, right? So if we did not restart the process after a couple of weeks, this issue would almost always happen, right? The latency increases, and it just like creates this problem. And this happened on a lot of machines and not just a few as what we believed before, because our metrics were a little bit off. The CPU on these machines was all normal. There was no anomaly there. The memory usage was also fine. Like that was like as per our models. And nothing abnormal was also happening at the network. So we had to start somewhere, right? So like because we modeled this enough, I had a hunch and we had a hunch that it was something to do with memory, and or at least like let's start with memory, right? But doing this was a bit tricky because the issue only manifested after 2 weeks or 3 weeks sometimes. And this is like I tried to reproduce this problem, for this talk, but it did not happen. I like ran like for hours and hours together. Just did not create the snapshot. So I'm not going to show you the snapshot here. Because it and the feedback and because of that, like the feedback loop was massive. And we have a clock running for BPD, right? So we had to do something, and we also had to. The other problem here was that we also had to ensure that the test bed is consistent, right? It sent the consistent throughput, mimicking what is happening in production as much as possible. So even that was a complication. And even though we weren't sure that the snapshots would help, we still sort of started with that as a potential case. So my notes are stuck. Okay, so when we did the snapshot analysis, again, I'm not showing the snapshot because I don't want it gets repetitive. There was one string that showed up quite a lot in the snapshots, right? A lot of strings, and that was contained by an array. The only place in the code base that was pointed to by that particular string, it sort of felt familiar, so I knew like where to look for. So I'm going to show that here in just a bit. So this is where I knew that this particular string shows up in the entire code base, right? And if you see here, like we are pushing something, something into a container object. So this is an array that's getting imported from a different module, and this variable is declared as a module variable. So effectively, it's basically a singleton, right? It's a global variable for the context of this application. So the array is getting ingested with these very small strings over time. And this gets iterated over and over, and like also you'll see that particular array, the CSS chunks array, I'm sorry, I don't have place to do anything here. So this CSS chunks array then gets like iterated over, right? And then like we figure out like what CSS modules that we have to include in the handlebars template. That's this code, right? So if you notice like what's happening here, we're not checking if the current chunk was already ingested before. The idea of the author here was to maintain a unique set of values, but it got missed out during all the things that happened. In the snapshot, there were about like 65,000 strings, by the way, in that like one array. So this was not causing memory bloat, which we can notice from just some monitoring UI, because the string size is very, very small. The iteration itself also doesn't take a lot of time because sort of it's like JavaScript is fast enough not to show it up as a CPU usage blip in production. It would have shown some impact in the load test, but again, because we cannot run a load test after 2 weeks of ingesting some data, we were not able to like figure out from our local local performance tests. It still caused a latency impact since the event loop is blocked. Like even though the for loop is very simple here and it is fast enough, but it still runs on the main thread. So any request that was coming in, any request that was going out was not getting, was not working the way that we expected to. And that added up to the latencies basically. Oops. Back to Keynote. So this is the fix. Basically, either use a set or do this like short-term fix that we did to find the string first and in the array and then like only ingest this. I'll see how long this will survive. By the way, this code existed for 3 years in the code base. It was running in production for 3 years before this was a problem. Just like slowly, eating up CPU cycles and massive increase on latencies after like a couple of weeks. Now this did not manifest any time before. Like 3 years, like we have been like running 3 BBDs basically, but this never manifested before, and it only happened this year because of a thing that is out of our control: sales. This year we had a different schedule for sales compared to last year, which meant that we were not deploying that often because like we sort of like don't do deployments before and after sales a little bit. So we were not deploying that often. And that's why the issue manifested only this year. It's kind of like was a surprise, to be very honest with you, at that time. So having a mental model of the application performance and the performance data that we can refer back to going back months and years made figuring this out like very systematic and quick, right? Like we did only like one iteration over figuring out what that is, and like we hit the target, which for me makes me very happy. So you see the difference also. Before, the response times on an average were like 1.89 seconds. This is on the test environment, by the way, not production, which we were running for 2 weeks. The second one is like what we would expect to happen, like 500 ms. This again, like after 2 weeks. Like time is a weird thing, right? It does things to us and our applications. Without that variable, this issue wouldn't have happened, or like we wouldn't have even seen this issue. So in both cases, my very basic understanding of memory snapshots that I learned from my previous company helped debug production issues and many more in between. Especially the first one, it's very close to my heart because I think that's the first time I was doing random things on the memory snapshot, but then I did discover that this was the issue. So, and then it helped, fix this issue, and like our BBD was okay at that time. So it's kind of a very nice bookend for so far for my career in Flipkart front to the latest one. And it's kind of amazing, sort of like very interesting to me that we have access to such powerful tools. If you just imagine how you would build the Chrome Dev Tools, for example, it's like just crazy. The amount of data that they show also is very interesting. And the fact that we have this for free and like license free effectively the moment you install a browser, which everybody has already, it's kind of really amazing to have. And I'm really grateful for the teams behind all of this. Because they make my job easier and sometimes even fun. So that's my talk. My name is Kashyap, and you can find me at these 2 places. And that's my talk.